Okay, folks, let's get started here. Comments on the test. I didn't realize that y'all couldn't see the grades. I'm sorry. I must have not gotten the settings right on iLearn, and so I'll go back and get that worked out so that you'll be able to log into iLearn and see your test and see what you missed and all that sort of thing. I have one person who's not taken it yet, having some family problems, and I think they're going to take it later this week. So we'll go over it once, and we'll talk through it in detail once I get everybody that's taken it. So I'll try to get that done, and I'll email you when I'm sure that you have access to it. I apologize. Usually there's so many settings. There's so many settings in iLearn, and if you don't click the right box, then it doesn't happen. So I've not had this problem before, but hey, stuff happens. Okay, so for announcements, we're going to have our pump reading quiz a week from today, and it'll be at the start of class. I think it's 20 questions. I want you to read. I think I told you this section, but I'll verify the page numbers and email that out. But that kind of like, I think it's improving pump performance. PDF, it's US DOE, it's downloadable from US DOE, but it's a really good introduction to pumps and just kind of the whole area that we're talking about. So it'll be a short, you'll probably have 15 minutes or something to do 20 questions. A lot of it's true, false and stuff like that. So, I mean, I wouldn't, if you read it, wouldn't anticipate anybody having any problems with it. So that'll be a week from today. So I'll give you some time to look over that stuff. Okay. So, we've been going through pumping stuff, and we're going to jump back into the presentation here in a little bit, but I thought I would just kind of give us a little bit of a break. What I put on the screen here is the old PSAT, PSAT, which I think this may still be downloadable. If it is, I would really recommend that you download this. Pumping System Assessment Tool. This was the first of DOE's really good pumping programs. Now there's a pumping module that's in Measure, and what's in there is fine. It's a number of different screens, whereas this is basically just one screen with a little bit of background information. I have a lot of experience using this one, and once you know how to know one tool, you don't ever really want to change to another one because you've got a learning curve that you got to go up. But I thought I would take a few minutes and just talk through this one because we're going to see similar capabilities in Measure. And I think probably, I don't know, on Thursday, I'll probably pull up Measure and show you it. And then eventually we'll have some sort of a homework problem associated with it. But so this is just a really nice calculator sheet. It's actually written, I think, in LabVIEW. But if you download it, it will install everything that you need, and you just fire it up. So it'll do two separate pumping analysis side by side, condition A and condition B. Generally, you probably will do like condition A before and condition B after, you make some sort of a change to the system, but you don't have to. They could be two completely separate. It's just, you've got, one pumping system in A, and it could be a completely different one in B, and it's up to you. This thing, it just does, calculations for you. They're not that hard to do by hand, but it sure is nice to just plug in numbers and bingo, the results appear on the screen. And the more you get away from working homework problems, the more you get out there in the real world trying to work on things, you really appreciate having tools that make your life a lot easier. So with that, we'll just start down through condition A. So these are pump types. So these are all of the different types of pumps that can be modeled with this software. And, you know, some of this is probably, you know, we haven't talked through all of this stuff, and we won't talk on all of these, but the different pump types, in suction, slurry, sewerage, API's American Petroleum Institute, double suction, you're pulling fluid in on both sides of the impeller. We could have a multi-stage boiler feed water pump. And your steam systems, high pressure steam systems typically have multi-stage pumps. In suction, that's kind of the one we just typically kind of default to. That's probably the most common type of pump. We got axial flow. Double suction would be larger than the in suction. Vertical turbine, the motor sits up high, and there's a shaft that extends down into like a tank, or they call them a hot well or a cold well. And you have multiple impellers on that rotating shaft. Those are called vertical turbine pumps, large end suction, and then you can also just specify an optimal efficiency. We'll just stay with this one. So then we have information. We have information on the pump, the fluid, the motor, the how much time it operates, and the cost of electricity, and then field data, hopefully things that you've gone out and measured in the field. So those are all of the inputs. Pump RPM, this could be a rated RPM, or it could be a measured RPM if you actually measure it. It's probably better to measure it. And you just put in whatever number that you have here. We can run direct drive, where the pump and the motor are coupled together, the same shaft, basically, or that you have a belt drive. And if you have a belt drive, you have belt losses, and this has a fairly typical curve built into it to predict the belt losses. That would be, you know, part of the energy use in the system. Kinematic viscosity and centistokes, you know, what fluid are you pumping? Specific gravity, what fluid are you pumping? Number of stages. Generally, you probably have a single stage pump, but you could have a 5-stage boiler feed water pump easily. Fixed specific speed, what this refers to, when you look at, and then these are the outputs over here. So these 3 columns are the condition A outputs. And you see you have an existing, so that gives you all of the numbers based on what you're actually doing over here, the inputs that you put. The optimal, it will take your flow and head, and it will calculate, it goes and it has some algorithms in it. So what is the most efficient pump that it can find in its algorithms that can push that flow at that pressure, at that head? And so that's an optimal configuration. And so then it will show you, well, this is what you're doing. And like in this case, I don't know, we're seeing 72.6% efficiency based on these measured conditions. This program can see a pump that could do this same job with an 84.8% efficiency. Oh, wow. Yeah. Now, most of the time, you don't wind up replacing a pump because that's pretty expensive. You know, most of the time, we're looking at maybe doing, putting a variable frequency drive to slow it down, or maybe we're going to trim an impeller to make the pump a little bit smaller because it may be oversized, in which case, many times you don't actually use this optimal column, but it's there for you. Now, back to this button, fixed specific speed. If I say yes, basically what it means is I'm going to stay within that same type of pump. If I say no, it's going to search all of the different pumps that it has. But the downside is if you do that, it doesn't tell you what type of pump it found. That probably is a downside. And for example, a lot of times these vertical turbine pumps are very efficient. But the problem is, if I've got a pump sitting here with a pipe coming in and a pipe going out, I can't replace that with a vertical turbine pump. I got to dig a hole in the ground and put a well and fill it up with water and stick a vertical turbine pump up there. I can't do that. That's never going to happen, you know? So if you were designing from scratch, then you might say, okay, wow, I can get 84.8%. Let me call up my pump supplier and try to figure out what kind of daggum pump that is, and maybe I'll design my system around it. But if you're working on an existing pump, you can't do that. Okay, so this says yes, which means I'm going to stay within the same type of pump. Now, watch what happens if I click no. If I just click this button, it says no. Oh, my optimal efficiency went up to 87.1%. But I have no idea if I could use, I don't know what type pump that is, and I don't know if I could use that type pump. So, you know, and now you could find that out. If you call up some pump suppliers, you could look around at that flowing head. You could shop around a little bit, and you could figure it out pretty quick. But so it's probably more conservative to leave that on yes and accept a lower optimal efficiency, which you can be pretty darn sure it's the same type of pump, one that you could actually, if you wanted to replace one, if this thing was old and falling apart, then you could buy one with, you know, 85% efficiency, put it in there, and you can include those savings in your calculations. So that's kind of what that is. And that refers to pump specific speed, which we'll talk a little bit about that. I may dig up a YouTube video. There's some good YouTube videos on that out there. Let y'all watch that. Line frequency, you know, it's either going to be 50 or 60 hertz. Or in the US, it's probably going to be 60, or it is going to be 60. And then horsepower, you got all kinds of different horsepower. You can specify if you have a strange situation. We can go all the way up to 50,000 if we want to. Wow, that's pretty significant. Motor RPM, it could be different than the pump. If you've got a belt-driven system, you know, you've got a pulley ratio, the motor could be fast, you know, faster or slower than the pump. Just depends on the pulley ratio. Let's see, energy efficient, the class of motor. So it has energy efficient, standard efficiency, average efficiency, and really, or you can specify if you have information on your particular motor efficiency, then you can put it in there. And, you know, so you can look, let's see, motor efficiency, probably right here. So it says 95.7 on energy efficient. If I go to standard efficiency, it's going to drop to 94. If I go to average efficiency, it's going to go to 94.8. It's kind of in between the two. So, you know, whatever you think. Voltage. And this is FLA is full load amps, and it would be the estimated full load amps at whatever voltage you put in here. Most motor tags say 460. You could be in a plant that was running 480. You could put 480. Say at 460, if I hit this, motor current 217.5. If I go up to 480, then it should, voltage goes up, current should go down. Estimate full load amps. Where'd it go? Where'd it go? Yeah, to 16.4. So it adjusts right in here. It adjusts based on the voltage. If you have a motor tag, you can put in your own full load amps. You may be able to read it off a motor. Size margin, many motors are sized with a service factor. I don't know if we've talked about service factor in here. You look on a motor and you see they're stamped on the tag. It'll say SF or service factor. A lot of times you'll see a number like 1.15. So what that means is that motor can be run at a 15% overload successfully, supposedly. It's probably not a great idea, but it's supposed to be able to do that. So if you had a 100-horse motor with a 1.15 service factor, it would be capable of outputting 115 horsepower. So that's what service factor is. And so in this case, if I had that, I could put a service margin in here of 15%. I wouldn't put 115, I would just put the 15 in here. Operating fraction, that's the fraction of a year in terms of hours. So if this thing operates continuously, I put in 8760 hours per year. If it operates, 2,000 hours a year, you take 2,000 divided by 8760, and whatever that fraction is, you put it in there. The next is the dollars per kilowatt hour. So right now, it defaults to 5 cents a kilowatt hour. If it was 10 cents, you'd put in 0.1, whatever. It does not do consumption and demand separately. That is a potential criticism. You get a better analysis if you separate the demand and the consumption, but that's not designed into this. Okay, and then we get down to the field data. So we've got 2,000 GPM. So we took and we strapped the ultrasonic flow meter on there, and we actually measured 2,000 GPM. It's best if you can actually have a good flow meter and measure it. You got to do the best you can. Head, that's the total pump head. Right now it's sitting on 277 feet. And we need a power measurement of some sort. This power, we can tell it I know power or I measured current and voltage. It's better to measure power if you have a power meter. So we're saying that we measured 150 kW and the measured voltage was 460. Okay, and so out of this, we get a pump efficiency. So let's see. So let's think about this. How could we calculate a pump efficiency? Well, let's think about this. And let me see. I'm going to try a new trick here. I don't know if it's going to work very well, but we'll see. I'm going to do a blank PowerPoint here. And, okay. So pump efficiency, well, this is a title page. I don't want this. Let me just put in a new slide. There we go. Okay. And we'll get rid of this guy. We'll see how this works. Okay. So pump efficiency is equal to what? What's the energy that appears in the fluid, which I'm going to call water horsepower, divided by the shaft power that comes into the pump from the motor, which we call the brake horsepower. Okay? Now, what's water horsepower? We had an equation is equal to, well, let's see, it was GPM times feet head times specific gravity divided by, and we'll divide it by a bunch here, the 3960, which are a bunch of constants. Lord, don't ask me to derive 3960 today. I can do it, but I'm not prepared. I need to do that. I'll try to do that for y'all next time. Times the motor. Yeah, so all of this is in the the numerator and the, what's the one on the bottom? The denominator. I couldn't think of that big word. It's been a while. Times the motor efficiency times the pump oh no, that's not right. Divided by 3960. Yeah, that's it. I don't even need the, well, I already got it. Okay. Yeah, that's the water horsepower. Okay. So we got a certain GPM through the pump. It picks up a certain feet of head going through the pump. And then if the specific gravity is other than 1, we multiply by that. And then we divide by 3960. So that's the water horsepower. Okay, so brake horsepower. Whew. Okay, we think about this as coming from electrical measurements. Okay, so if we take the motor power, motor kW, and this equation up here will give horsepower. I guess we probably should indicate this in horsepower. So if we take the motor kW times 0.746, that converts the kW to, let me see, horsepower. Now I got to divide. I didn't know I was going to do this. Is that right, kW? Yeah, because it's 7.4, that's kW per horsepower. So when I'm going backwards, I have to divide. Okay. Motor kW. Put some parentheses around this. Okay. And so, okay, so that's the power into the motor. Okay. But part of that is eaten up by the motor efficiency times. And these efficiencies are in fractions. And times any drive efficiency, if any. Okay? So the assumption in PSAT is that you're going to measure that motor kW. Now, if you have to measure volts and amps, if you have to do this, then kW what is equal to what? It's volts. And that would be an average of the 3 phase-to-phase measurements times amps times SQRT square root of 3 times power factor divided by 1,000. So if you're forced to take the volt and amp measurement, you do your averaging and then times the square root of 3, and then you got to go find a power factor, which has some stuff built in PSAT for that, and then you divide by 1,000, and that gives you kW, and then you divide that by 0.746, and that gives you your input motor horsepower multiplied by motor efficiency and a drive efficiency, okay? So, there you go. Now, let's go back to PSAT, and let's check this. But see, PSAT's going to do all this for you. Now, let me get out my calculator. And so, we got, what, 2,000 GPM times 277 feet ahead. And specific gravity, this is just standard water, so is 1 divided by 3960. So that's 100 and about 140, 139.9 horsepower. Store one. I don't think it gives you that number. Okay, but we've got 150 kW. So 150 kW, and so if I divide by 0.746, that's 201.1 horsepower. So, you know, it's right there. And then I've got a, let's see, I'm direct drive, so I don't have a drive efficiency. And this thing gives me a motor efficiency right now. It's got 95.7. So times 0.957 is equal to 192.63. Store that away. And so then if I ratio those, it should give me roughly 72.6%, which is my pump efficiency. So recall 1 divided by recall 2, and 72.7. So there's a little bit of rounding digits. But so basically, that's all this is doing for you, is those simple calculations. But wow, put in the thing, bam, you got it. And you didn't have to look up a motor efficiency because it pulled one for you. Okay, so that's pretty nice. So if you look down through those outputs, so we get an existing efficiency. That's just our rated motor power. So this shows the, oh, okay, it shows you the motor shaft power. Okay, so that should be, well, it should be the calculation we did from this converted to horsepower times the motor efficiency. The pump shaft power, now notice they're the same. If I change to belt drive, oh, how about that? It changes my pump efficiency. See, that increases my pump efficiency if I change to belt drive. Because look what happens. So it's got a, this is probably like a 2 or 3% loss. I'm not sure. It's got a curve in there. So I have the same shaft power, but I'm losing some power across the belts that doesn't get into the pump. So the pump is producing the same flowing head with less power, so it has a greater efficiency. Well, that makes sense. Okay, let me see. Let's calculate what that belt loss. Let's see. So what is it? It's 92.4 minus 84.7. So we're losing 7.7 divided by 192.4. Yeah, it's 4%. So it's assuming a flat 4%. Now, that's not perfect at all. It depends on the type of belts and a lot of things. But anyway, that much is built in there. So if we say, nah, we don't have belts, we're just playing around. So then the power that comes out of the motor goes directly into the pump. So they're the same thing, which is appropriate. Motor efficiency. Oh, power factor. That's interesting. And then it shows you a motor current. So it takes this power measurement and it backs out what the motor current would be and shows you that. That's the power. It just repeats. You told it you measured 150 kW and it believes you. It will believe you every time. Whether you get it right or not, it will believe you. And then, so this is the annual energy in megawatt hours. So, and we got the operating fraction is 1. So this would be this motor KW. Let's see, we got motor rated power. Oh, out here, it's a 150 times 8760 divided by 1,000 to put it into megawatt hours instead of kilowatt hours. So that's the annual energy, and then that's the cost at 5 cents. So $65,700. Okay, now let me show you the background information. If you click this little box down here, background information, you got some pretty cool stuff. This is my favorite, motor performance curves. So looky here. So here you get information on power factor. We get percent full load amps, and we get motor efficiency as a function of the load on the motor. So see down here, we've got shaft load as a percent of rated. So right now I'm sitting on a 200 horsepower motor. If that thing was 50% loaded, if it was putting out 100 horsepower, then let's see, this is my percent full load amps. At 50%, my percent full load amps is 55.49, which is right here. My power factor is 78.71, which is here. And my efficiency is 94.95, which is here. So this is great. I use this probably more than I use PSAT. All of this stuff is produced by curve fits from the major motor manufacturers. And so it's not perfect, but wow, it's a really good, quick place to get a reasonable number that has some pedigree built into it. Because the guy that did this, Don Cassida, did all of this, and Don Cassida is as good as it gets on pumping. He's first class. If Don puts it out, I've been in a few arguments with him, and I don't think I ever won one. We used to travel together for Alcoa some. We get into these discussions, and every time I had a disagreement with Don, I wound up being wrong. After about the third one, I just quit. I quit arguing with him. I said, "Okay, Don, if you say it, I'm gonna believe it." You know, hey, I'm not gonna get my tail chewed the fourth time. Anyway, so this is pretty good, and you know, you can change the efficiency class. You change voltage. It'll change a little bit. So anyway, so that's pretty cool. Okay, click to close background window. And there's a few other things in there you can look at. Okay, let me show you this. Here is the head tool. So this will calculate a pump head for you based on measurements out there in the field. And we actually have two different geometries that we can work from. This is one where you have a suction gauge and a discharge gauge. This case of S would be some components. It could be a valve. It could be a shut-off valve that's wide open. It could be a strainer. It could be just any piping component that's in there. That's the case of S is the summation of the loss coefficients that you have to, you know, it could be some elbows. The pipe could bend, you know, before from the gauge to where it actually gets into the pump. Okay, so that accounts for pressure losses between the gauge and the actual pump itself. Likewise, you have the opportunity to put in some loss coefficients from the discharge of the pump to the gauge, because there could be some losses in there. And so you know, if you don't put that in, the pump is actually putting out more pressure here than you're measuring here, and you're shortchanging the pump if you don't put that in. This would be a flow measurement, and then we have elevation, say from some datum, usually the floor or the ground or something like that, if there's a difference in heights of the gauges. So that's one geometry. And then oftentimes in a plant, you see a situation like this, where you're pumping out of a large tank. And so then this would be called a suction tank. And so we would maintain some elevation in the suction tank, number of feet above this datum. And so here, sometimes you don't have a suction gauge. So basically, we calculate, you know, any pressure here above atmosphere and this elevation of water to calculate the pressure at the suction of the pump. So you use this if you don't have a suction gauge, basically. or you have to measure or start guessing or something. But anyway, so if you look at this, this is really pretty nice. So on the suction side, you've got the pipe diameter. Take your tape measure and measure it. Your suction gauge pressure, in this case it was 5 psig, the elevation of the suction gauge, and then the suction line loss coefficients, in which case that's probably some sort of a valve that's wide open. Just, you know, because you usually have valves on both sides in case you got to take the pump out. It's real handy to not have to drain the system of all the fluid. And then on the discharge side, we have a discharge pipe diameter. And notice it's common, not always this way, but it's common to have that discharge pipe a little bit smaller than the suction pipe. And that's to minimize the pressure reduction on the suction side of that pump so that we don't get into a cavitation situation. So that's pretty common. We have a discharge gauge, it's reading 124. Right here we have a discharge gauge elevation. Right now this thing defaults to 5 feet on both sides, but you can change that. And then your discharge line loss coefficients would be case of D, which would be 1. We put in a specific gravity and we put in a flow rate, and bingo, this calculates my pump head. So that's where, that's the head that I would be generating on that pump curve. Wow, that's pretty nice. Now, you will get an opportunity to do all of this by hand. And after you do this by hand a couple of times, you really appreciate this calculator, because it's not terribly difficult. It's all fundamentals, but it's probably going to take you 15 minutes to calculate that pump head. When all you got to do is stick numbers in here, and bingo, you got it in about 20 seconds. It's real handy. So then it breaks it down into the different components that go into the total pump head. So for example, it says differential elevation head 0, but let's tell it that this gauge is 10 foot in the air. Oh, well, guess what? Now I've got a differential elevation of 10 feet because this gauge is 5 foot higher than this gauge, and that pump had to push that water up that 5 feet. So that's an additional 5 feet of pressure that pump, and that's before I measured it. So that was additional pressure that pump had to generate in order to produce those measurements, okay? Differential pressure head, well, gosh, what is it? It's for standard water, what, 1 PSI is 2.31 feet, roughly. So if I take this delta P, which is what, 119 times 2.31, it's 274.9. 274.99. So I'm off a tenth. So Don's got some extra digits in there. That's just doing the numbers for you. Differential velocity head. Well, so the kinetic energy is greater in the discharge pipe than the suction pipe because the diameter is smaller. So that's V squared over 2G. You can calculate V squared over 2G if you want to, but why bother when this will do it for you, other than on your homework. Estimated suction friction head loss, 0.25 feet. That's from that suction line loss coefficient of 0.5. So that's V squared over 2G on the suction side times 0.5. And the discharge line loss on the discharge side is 1.04. I add all those up, and that's your pump head. Okay. Now, let's take a look at these little notes. Important note about loss coefficients. That's a lot to read, but we need to read it. Because about 3 years ago, I ignored this. I forgot about it. And I had a student, he turned in this big homework, and I went over my homework solution, and this student raised his hand and said, well, Dr. Cunningham, what about this note? Because he read it. I went, what note? What are you talking about? I hadn't read that thing in 10 years. I forgot about it. And so I went, and I'd gone through my whole solution, and he basically proved that a portion of it was wrong because of this note. So I remember this now. The loss coefficients used here apply to the velocity head in the line size represented by the suction and discharge pipe diameters at the points of pressure measurement. If the loss elements are in different size lines than the points of pressure measurement, they need to be appropriately scaled. It is generally suggested that the losses be scaled in proportion to the fourth power of the diameter ratio. And when you start taking things to the fourth power, they get big pretty quick, or small pretty quick. For example, if the discharge pressure is measured in a 12-inch header, and there is a 6-inch check valve with a nominal loss coefficient of 2 applied to the 6-inch valve, the K factor used for the valve would be 2 times 12 over 6 to the fourth power, or 32. Oh, from 2 to 32. That could go up pretty quick. Oh my. The reason for this fourth power scaling is that the velocity varies with the square of the pipe diameter, and the velocity head to which the loss coefficient applies is proportional to the velocity squared. So you got to be a little careful with that. But anyway, so depending on the configuration that you're working with. Okay, so that's that. We'll leave that unchanged. All right. That's pretty much for this right now. I mean, for example, what you can do is, let's say this was our base case. You can go copy A to B, which is nice, and it just makes these two the same. And then let's say that, let's say I've got a valve that's throttled in this thing. And I calculate by some methods that will come up. Maybe I've measured the pressure loss across the valve. So what I'm going to do is I'm going to trim the impeller, because the pump's too big, so they got the valve, you know, like 50% shut, okay? So I'm dropping a bunch of pressure across the valve to move me up the pump curve, okay? So by hook or crook, I figure out what the pressure loss is across the valve. And so let's say that, and all of that's in there in this 277. Let's say that I think that by opening the valve and trimming the impeller, I can drop that 277 feet to 200 feet, because I'm dropping 77 feet across the valve, okay? So I can open the valve, trim the impeller, and reduce my head in the system by the 77 feet across the valve, okay? So what I've done is everything's the same, so let me change this to 200, okay? Now, if you look at A to B, so I'm existing A to existing B. Well, now just a minute. I don't look so good. I'm using the same amount of energy. But I have to somehow project what the power is going to go to, because I've still told it I'm using 150 kW. Well, if I'm generating 77 fewer feet of head with a pump, my power should fall. Now, then you got to come up with a way to predict that. One thing you can do, you can look on the pump curve and see what the efficiency should be. Let's say I look on the pump curve, and it looks to me like when I trim that impeller at this operating point, it's going to give me a 75% pump efficiency. Okay? So then I come in here and I look at this. Well, that's not 75%. Well, so how can I make that get bigger? Well, I can reduce the power. I can guess the power until I make the efficiency 75%. So, I don't know, let's just put 100 in there. Well, 78, not quite that good. Whoops, 100 point. That's pretty close. So my projection would be, I would be saving about 45 kW And now my cost of operation is $46,000 a year. So rough and dirty, 65.7 minus 46, that would save $19,700 a year for trimming an impeller, which I can do in a half a day and probably take it down to the machine shop, if at any kind of a plant with a machine shop, and tell the guy you have to do the calculation. Say, here, take the pump apart, take the impeller out, take it to the machine shop. Here, cut 5/8 of an inch off of this impeller and polish it up. Put it back in. Pump is smaller because the impeller is smaller. Open the valve, measure the flow rate. Hopefully you still get 2,000 GPM. If you get 1,700, you get to buy a new impeller because you cut too much off. Maybe you should cut it off in stages, you know, I don't know. Or you could talk to the pump manufacturer and get his recommendation on how much you should cut off. At least if you cut off too much, you can blame it on him instead of you when the boss has to buy a new impeller. No, but you know, there is always a danger. Or you could put a variable frequency drive on there, and then you could put it wherever you want it. You just slow it down. Oh, that's too much. Okay, well, I'll speed it up a little bit. Yeah, different ways to do this. So anyway, that's an example of kind of the capabilities and the what you can get out of PSAT. And there's other stuff you can do, but that's pretty good. Well, that worked out all right. All right. All right, so I think this is where we left off before. I know it's been a little while. We were going through these different types of pump curves. And this one, I don't think we talked about this one. This is the vertical turbine pump. You know, before I do this, let me just go off here. Let's take a look at a vertical turbine. So you, oh yeah. There you go. This is what vertical turbine pumps look like. Oh man, they got all kinds of them. Yeah, they're typically pretty big. I mean, I've seen these things 500, 700 horsepower, something like that. Let's see. There you go. So your motor mounts up here on top of it, and this flange that is like mounts on a concrete deck, and then this shaft it extends down. I mean, some of these things, this shaft could be really, really long. Now, the typical one, that might be 10 to 20 feet. And it sticks down into this well, and each one of these, they call them bowls. This would be a 3 impeller situation. So this would be like a 3-stage vertical turbine pump, something like that. And you can add stages. You can have 5, 6 stages. Some of them only have maybe 2 or 3. It just depends on the application. But that's what we mean by a vertical turbine pump. Oh no, I knew I did that wrong. What do I want to do? Hit the wrong button. There it is. Correctable error. Let's try this one. Okay, so now you start working on these, you got to be a little careful. I've gotten myself little messed up before on these things. So notice, this is the bowl head. So if I had 3 bowls, I would get 3 times the head. Okay. Let's see, and we also get, these are 3 different sizes, A, B, and C. And we got, here's the horsepower per bowl. And this is, there's a flow rate down here, which I'm not seeing displayed on the slide right now. And here is the efficiency. And so if you were selecting, say right here on this 60 feet of head, say you were right here, whatever that flow rate is, you have the same flow rate through each bowl, but if you had 3 bowls, you would have 3 times 6, you would have 180 feet of head, because it goes through one and then it goes through the other and it goes through the next, and each one boosts the pressure by that amount. Okay, and so it also affects the efficiency determination. So from these numbers, if you have just 1 stage, you have to deduct 2 percentage points. If you have 2 stages, you deduct 1 percentage point. And if you have 3 or more stages, you don't have to deduct any efficiency points. So it's kind of interesting. So if you're working with a vertical turbine, just be real careful to read whether it's a total for the system or whether it's just per bowl. Because see, this is the horsepower per bowl. So if you had 3 bowls, you know, you might be up here around 60 horsepower. You'd have to have a 200 horsepower motor. If you had 1, you could get by with a 75 horsepower motor. You know? Okay. Here's just some curves on a submersible pump and combined pump motor efficiency curves. So these are efficiency curves. You can read efficiency over here. And it just shows, like this might be a selection point. This would be the pump by itself, but when you consider the motor inefficiency, and so that would be the combined efficiency. Net positive suction head required is over here and read on this scale, 36 feet. And I guess this is the actual pump curve over here, or flow versus head. Interesting. So where does a pumping system operate? At the intersection of the pump curve and the system curve, where those 2 things come together. So, oh, that's what I didn't show you on PSAT. I knew there was something else. I did. We're going to have to go back. I don't want to cover that. I'm getting forgetful in my old age. System curve tool. Oh, yeah. You can, okay. So this is a system curve calculator, okay? And so what you do, specific gravity, you put in here. The exponent, and this system curve will be of the form, and we got some more slides on this, a total head H is equal to a static head, a static elevation. If we're picking water up down here, carrying it up to the top of the hill, that's a static head. I think we've talked about that before. And that's equal to this constant, K prime, times flow, Q, GPM, raised to a power, C, okay? Well, here's the power. Now, Don, who wrote all this stuff, says in his experience, he thinks 1.9 works better than 2. The theoretical stuff you see would be use 2 for a squared relationship. I'll show you, we'll play around with this for a second, and I'll show you, it doesn't make a whole lot of difference, you know, so you can pick whatever you want. In order to use this, so you pick whatever exponent you want. So right now, I'll leave it at 1.9. You have to have 2 points of operation that are on the system curve, okay? Well, one point is usually the zero flow point. Because at zero flow, the only head that you need is the static head in the system. So let's say that you had to pump from this tank to one up on the hill, and the difference in elevation from the free surface here to the free surface here is 200 feet. So at zero flow, you still requires 200 feet in order to get water from this tank to that tank. And it has nothing to do with friction. It has to do with how tall the hill is, you know? Okay, so that's what we call static head. So it's common. You don't have to. You can put in any 2 points that you know on the system curve, and it will fit it. But it's very common to use the zero flow point. If it's a closed loop, it's 0, 0, because a closed loop has no static head. Well, that's pretty darn easy. Put in 0, 0. Then you just have to have one more operating point, and that's usually the point you go up to the pump and it's operating. Well, that has to be on the system curve if it's operating on the system. And so you can take measurements on that operating pump and try to determine, you know, the pump head. We just saw how to calculate pump head, measure the flow, and you're good to go. So let's say, oh, that we just changed it a little. Let's say for our system, we had, let's say we had 50 feet ahead. There we go. So you get a curve like that. Well, I mean, that's all it takes. Here's my static head. It's whatever I put in at zero flow. So H sub S is 50. Here's my loss coefficient, my K prime is what, 1.21257 exponential minus 4. And there's my exponent. That's pretty easy. I can take that and I can put it in Excel and I can program that system curve all day long. Pick a flow and, you know, just calculate what the head is, plot it up, pick points off of my pump curve, plot it up wherever they meet, bingo. I got it. I got it put together. Okay, ignore changes. Okay, so we get a pump curve from the manufacturer. We get a system curve from our analysis of the system, and we plot them up on the same graph. Wherever they cross, that's where we're going to operate. Okay, net positive suction head. We've talked a little bit about that. Here's some equations where you can calculate it. It is the total suction head in absolute pressure minus the fluid vapor pressure is what you actually have. This would be a velocity term V at the suction of the pump, V squared over 2G, 2.31, assume standard water, but when I divide it by specific gravity, this converts from PSI to feet of head. So this would be the suction pressure. This is the atmospheric pressure, the second term. And this is any elevation head that you have behind it. This is the vapor pressure. And so those words are calculated in those equations. Net positive suction head required is, by long-term accepted practice, the available suction head at which the developed pump head has already dropped by 3% from the head that it produced with bountiful available suction head. So in other words, the numbers that they publish on the curve were already in cavitation. And we have lost 3% of the head that would have been developed if we had more suction head. That's the numbers they publish. So if you provide just what the curves on the pump curve say, it's really not enough. I would shoot for double that, or at least 1.5 times that. to make sure that I stay out of a cavitation situation. Now, you know, sometimes you got to do what you got to do, but you need to be aware of that. So when you look at those pump curves and it's got that NPSHR curve on there and you take your flow rate up and over and it says 20 feet, you got to realize that you're already slightly in cavitation if you just provide 20 feet. By definition then, the pump performance is already degraded due to cavitation-related flow disturbance. The actual point when cavitation actually begins can be with significantly greater available head than the pump supplier's NPSHR curve. And then there's comment there about measurement approaches, which I don't really care about. So this just shows you kind of a graphic. This shows you a head flow curve with plenty of net positive suction head available. And this is what has happened when I reduce it and operate just at the recommended curve. Say we've already lost that 3% at the point that they publish. So head drops by 3% at 1400 GPM when NPSHA is approximately 18 feet, which is what they're referring to there. So you really want to stay away from that the best you can. I'm going to skip this. Y'all can read over those. Let's go on to the affinity laws. Okay. So, you know, we talk about the fan laws, the fan affinity laws, and the pump affinity laws. So the appropriate use of these is to predict changes in pump curves, not operating points. These modify the pump curve or the fan curve, and where it operates is at the intersection of the modified pump or fan curve and the system curve, because the shape of the system curve affects the outcome in terms of operating points. So it's not just affinity laws, okay? These adjust the pump curve. This is what you need to know. Now, people use these things to predict operating points. And sometimes they get it close, and sometimes they screw the heck out of it because they don't understand that you have to take into consideration the system curve. I can have all kinds of different shapes of system curves. Okay, so all this does is modify the pump curve if I change speed, or if I operate at the same speed and I change diameter by trimming an impeller. So these are not appropriate for directly estimating operating points, only for adjusting pump curves. Okay, affinity laws aren't perfect for diameter changes, and Don points out here that when they're better for speed changes than they really are for diameter changes, but at any rate, you know, they get used for both. But so here's some data. This was what, 2008. Don worked at Oak Ridge for a while, just doing all kinds of testing on stuff. And so here's some curves, some pump curves, and you can see, so for, this is a 15-inch impeller. And so we see, this is the actual curve that he tested, and this is what the affinity law said for a diameter change. Started at 19 inches, and say if you trimmed it to 15, this was what he measured, and this is what the affinity law projected. So, you know, similar, but certainly not matching. At 17 inches, obviously, he hadn't trimmed off as much. So they trimmed off 2 instead of 4. So they got better performance. So for small changes in diameter, they're probably pretty good. At larger changes, maybe not so much. Consider trimming a trim and impeller diameter recommendations. Get actual performance curves from the manufacturer, especially if the trim change being considered is large. do a field performance test of the existing pump. And there's some stuff from the Hydraulic Institute that I'm not going to read over. Okay, but affinity laws generally hold up very well with speed changes. So this would be a pump curve that you would get the 100% speed from the manufacturer. And that speed would probably be something 1550, 1560 RPM, whatever they chose to publish it at, okay? And then, so at 90%, it would be 90% of 1550. This would be 80%, 70% as you slow that thing down. So you see what happens when you generate these curves in Excel. You take this curve and you pick points off of the actual published pump curve. So, you know, you would say, so, okay, 7,000 GPM, I've got 80 feet ahead. Put it in a table. 6,000 GPM, I got 111 feet ahead. Whatever. You pick all these points, you plot it up, and when you first look at it, it's kind of not so smooth. It's kind of bumpy, you know. And then you say, well, I'm going to scoot this one down a little. I'm going to scoot this one up a little. Well, you do a little engineering on it, and pretty soon you got this nice smooth pump curve that looks just like the one that the manufacturer. And you got to realize his curve, he took 10 pumps and measured the performance and averaged it all together. So the one that you got, that's been in the field for 10 years, you know, if it's not torn up, if it's not, the impeller's not damaged, it's relatively close to this, maybe. You know, so the fact that you've scooted a few points around is really not a problem at all, so long as you don't do something stupid with them, you know. So you get that point. And then if you want to run your 90%, you take each one of those points. Say I take this point, and okay, if I reduce the flow by let me see, what do I do? I adjust the if I go to 90% speed, I go to 90% flow. So I cut the flow in linear relationship with the speed reduction that I want. The head goes with that ratio squared. So then I would take 0.9 squared, which would be 0.81. 0.81 times this 80 feet of head gives me the head at this point. And so then this point will shrink down to this point. So you take all of your points and you shrink them down, and then you redraw the curve. And so you can plot a pump curve at any speed you want using the affinity laws, and that's appropriate. And then you put your system curve on there, and wherever that adjusted pump curve crosses your system curve is where you're going to operate. And that's the correct way to do the analysis. So anyway, but once you have that, and notice the other thing, so what does BEP stand for? What's BEP stand for? Best efficiency point. See, we got 85 on both sides of it. That's your best efficiency point. That's where the pump manufacturer would love for you to operate that pump. Real close to BEP, best efficiency point. But whatever efficiency point, they see how this point comes down here. Well, what kind of system curve? Where is that thing headed? Man, that thing looks like an all frictional curve that's headed for 0, 0. So see, and we have some more system curves on here. We'll talk about that in some more depth and detail. But when I take this point and translate it down to this with the affinity laws, the efficiency comes with it, pretty much, okay? So you can see, that's what he's done. He's taken all of these points and collapsed them. with the affinity laws. So anyway, so this says that, you know, if I cut the flow in half, or if I cut the speed in half, I cut the flow in half. If I double the speed, I double the flow. So the head then is that ratio of speed, which is the ratio of flow, squared, and the power of that point goes with the cube. And then the efficiency is to the zero power, which means the efficiency stays the same. Now, if I keep the rotational speed the same and do diameter changes, then so all of this column assumes the diameter is the same, and all of this column assumes that the speed is the same, and I'm changing the diameter. And so you see it's analogous in terms of the affinity laws to diameter. But as we said earlier, that it tends to work better with speed changes than diameter changes. That's how the power curves change. That's how the efficiency curves change. This is an example. I did this for a client at some point. I forget who it was. But so this is kind of how you go through it. So this system curve, well, first of all, you see it was an all frictional system, okay? Because it goes through 0, 0. Okay, so it had a throttled valve. So this was a design point on the system. So the assumption is when you open the valve 100%, your system curve is going to relax because it has less resistance, and you're going to come out here and you would operate at your regular full speed pump curve. You would operate here, which is about 2,000 GPM at, looks like about 90 feet of head. But when we go in and examine the system, you go, oh, look at this valve. It is pinch, pinch, pinch. I measure 1,400 GPM, and the pump head is 110 feet. Well, they managed to reduce the flow to what they needed, but they didn't do it very efficiently. Because if I open that valve up and slow the pump down, I can operate here instead of here. Look at it. Look at the reduction in pump head. That's what was that, 45 versus 110? You think that's going to save some energy? Daggum right. It's going to save a bunch of energy. And so that's what we're looking at here is, you know, you go out in the world. Well, in fact, we were at Wapaka Foundry. The two ladies in the back of the room were with us over break. We found 12 pumping systems or more. And we got pictures. I can show you pictures. I probably should show some of those pictures. Yeah, I got valves 20% open, 30% open on a, I don't know, what, 50, 60 horsepower motor or something like that. I don't know. Oh, no, but those were 200s. No, that's the fans. The pumps were smaller. I can't remember. I'm getting this stuff messed up between the pumps and the fans. We found a bunch of stuff. But anyway, I've got pictures of valves that you can see where that valve, if it was this way, it would be shut. If this is this way, it would be open. And it's sitting there about like that because the blasted pump is too big. So, anyway. Oh, what do we got next here? Yeah, this is a good point to stop. Y'all are getting that look like surely he's going to shut up one of these minutes. So I'll stop. And don't forget, a week from today, you have your quiz, reading quiz on